You might actually wonder why you would bother with worker, because up to now you can't do much more with it than you can do with a simple bash for loop that submits jobs. Or what you can do with job dependencies for the prolog and the epilog. So there are a lot of worker features that make it quite compelling to use, and we'll deal with those right now. So as promised, there is a lot of bookkeeping which you don't have to do when you're using worker, and a number of scripts, commands, have been written in order to accomplish that. So for instance, one of the bookkeeping things which you have to do is to keep track of which work items were actually executed correctly, which had problems, and so on. So you can get a summary of a job, a worker job, by using w-summarize. And then you just specify the PPS, the log file, which is generated during the job. And as you can see, that log file has the same structure in file name as your error and your standard output files. So basically the number which you see at the end of the file name is in fact supposed to be the job ID. So basically that works very similar to what you have with ordinary QSub. You would get a .e and a .o file for error and output. This you also get with w-summarize, but you get a couple of more files, and one of them is this log file. This log file is used to record which work items succeeded, which failed, and with what error code. It also gives some timing information, which is also useful for other purposes. So basically, you just get summary information about your job, and you can run this command when a job is done or while is it running, because then it also gives you some information about the progress of your job, what has already been done and what not yet. So what you can do, for instance, is use the watch command to run w-summarize periodically, so that you get you can follow up on how your job is doing. Of course, don't do this for days on end. The -n60 means that the command is done every 60 seconds, so every minute. But please don't overuse this, because it will actually load the login nodes, and basically that's not what you want, because it's a shared resource. Another thing which may happen is that your job actually runs out of wall time, for instance. And then of course some of the work items will have been completed successfully, while others were in progress or not yet started even. And of course, if you have to do the bookkeeping for that by hand, that's not so pleasant. So basically, again, worker is going to help you with that. There is a command w-resume that you can give any arguments which you can give to w-sub, and it takes a job ID additionally, and it will just restart the job, but of course work items that already have been completed successfully won't be redone. You can also redo failed work items. So a failed work item is a work item that ended with an exit code that is non-zero, which you typically use under Linux in order to indicate that something went pretty wrong. So by default, w-resume will not redo failed work items. It will only do things that were not executed yet. So if something failed, there's probably a good reason for that, and unless you take some action, you do something, you fix a bug, whatever went wrong, you fix that, then of course you can redo failed work items as well. And for that there is the retry flag. So w-resume doesn't do it by default, but if you're sure that a failed work item can now be done successfully, then you can just resume with -retry. Another thing is time limits. So basically there is of course the time limit of your job, which is the wall time, but that is the time that worker will run, so basically for all work items that it has to do. But you might want to limit the time an individual work item takes, and this you can do using another utility, which is called time to run, and that will actually monitor a running process, and once a given time is exceeded, it will just stop that particular process. So it is in fact independent from worker. You can use worker without time to run, you can use time to run without worker, but it offers some extra possibilities for using worker. For instance, one of the things which you really might want to avoid is that some work item accidentally keeps on running. For instance, you may have underestimated the time for an individual work item in certain circumstances, and you actually want to ensure that when a certain time is exceeded, that that particular work item is going to be aborted. And for that you can use time to run. So in this particular example, time to run is used to limit the time for the application CFD test to 20 minutes. Another task which you typically have to do is data aggregation. So in parameter exploration or in other settings, you might get a lot of output, and you would aggregate that output, for instance, in order to compute a mean value or to compute other statistical measures or what have you. So basically it is very often very convenient to have an individual work item create a file, and then later those must be combined into one file later, and that can potentially be a bit of a pain. So if you use file names that are based on values in the data, then it actually gets a bit easier. So for example, consider the data.csv file which is given here. There is a parameter a and a parameter b, and each of those are real numbers. Then basically you might for each row have an output file, and the name of that is based on the values of a and b. So basically for the first row we have a equal to 1.3, b equal to 5.7, and that is reflected in the first output file, output dash 1.3 dash 5.7. So this is a possible approach in order to do that. But then again, you need to combine a lot, and that might be a bit problematic. So wcat can actually help you do that. So it is intended to do more or less automatic data aggregation. So it takes as an argument the data file which you used with the w subcommand, and then it takes a pattern, and that pattern is in fact representing the output file names. So in this case it says output dash, and then in red here, so the first square bracket thing is the value of a, and then again a dash, and then the second pair of square brackets, that is the value of b in green here, and .txt. And the final output file, so the aggregated data, is going to be in output.csv. And one of the things you can do is skip lines in each individual file. So in this case we skip the first line, because for instance it might contain column headers, and we only want those once. We don't want them in every so many rows, as there are lines in the individual output files. So wcat will in fact do that pretty much automatic for you, and basically you will be able to do that easily. And the nice thing is that the output in the final output.csv file will be in the same order as the data in your data.csv file. So basically the order is in fact preserved, it is respected. And you can do that either from the worker epilogue. using the -epilogue option, or simply from the command line after your job has run. So wcat is pretty simple, it just concatenates files. Sometimes, of course, you have reduction that is more complicated. And for this, wreduce can help. So it's for more general data aggregation. The idea is essentially that you again specify the data.csv file, which you used in order to submit your job. The pattern is the same thing as before, nothing changes, but the output file is specified, but there is a reductor. And the reductor can be any script. Now, the reductor actually will append new data to an existing file. So it takes two command line arguments. The first one is the name of the file with all the output data up to that point. And the second argument is the name of the file to append to that output data. So that's basically the idea. It is the reduction operator which you have in many programming languages or also in parallel programming. And here is an example of a Python script that is actually a pickle reductor. So basically, the pickle is a format to serialize Python objects, and this can be used in order to serialize things. So basically, it has, as said, two command line arguments. One is old, so that is essentially the file that contains the data up to that point. And then new is the data which has to be added to the aggregation file. So the first thing to do is to read the aggregated data, then to read the data to add, then the data is added to the data structure, and the updated data structure is written as aggregated data in a new pickle file. So that's basically the idea. And this is executed for each data item. Another thing which is interesting is workload analysis, and that means load balance. Do all the workers do approximately the same amount of work? And of course, if all work items take the same time, yeah, that's easy to answer, but what is the distribution? And can you improve things for another run by taking a different number of workers, something like that? And to do that kind of analysis, wload is quite useful. So you can get a report on the work items. That's one point of view. So basically, how long did it take to compute individual work items? Or you can take a different perspective. You can ask for a report on the workers. So how much work did individual workers do? And so basically, depending on the command line option which you provide, you will get results. And for this, again, you use the log file of a run of a job which has been run with worker, and the command is wload. So load balance, basically there is a remark to make. So for instance, wsub-l nodes is 5, ppn is 36. In total we have 180 cores, and you might think that there are 180 workers, but that's not the case. There is one master and there are 179 slaves. So the slaves are doing the actual computations. The master rather, is doing the coordination. So basically, if you are not aware of that, you have one slave less than you might expect. So that means that in total 197 work items will be executed concurrently. There is a special flag which is -master, and again we have nodes is 5, ppn is 36, so in total we have 180 cores. But now, using the master flag, there is one master process and 180 slaves. So basically, this might be more what you inspect intuitively, but it is actually optional with a very good reason. The reason is essentially that this violates the MPI standard. So it works, but it kind of works by coincidence. Obviously, I've tried this with quite a number of MPI implementations, and it works with all of them, but still I'm a bit reluctant to make that a default, because basically I'm doing things I shouldn't be doing. So another thing which you can do is use WSUB, but use multiple data sources. So for instance, you have a number of files, data 1, data 2 to data n, and all of those contain data, and that needs to be used, each row of those files, all those files needs to be used in the file. And this again, you can do easily. You can even combine it with the -t flag to get the PBS array ID, and at the end of the day, you will have as many work items as the minimum in data 1 to data n, and of course the -t flag. So that's basically the idea. And this of course helps a little bit in certain situations, because you don't have to combine separate data files, you can just use them as is. So that can be convenient from time to time. There's also support for rather non-trivial scenarios, because a few environment variables are exposed by worker in the work item shell. And examples of those are worker size, so that gives you the number of worker processes, and worker rank, so that would be an identifier for an individual worker. This can sometimes be useful in order to divide work among workers and to ensure that there are no conflicts.